Good morning to all of you. In previous session, we have seen IR filter designed by approximation of derivatives, which is also referred as backward difference of derivatives, where we have used the mapping function as small s is equals to 1 minus z inverse 1 plus z inverse upon capital, 1 minus z inverse upon capital T, right? So in today's session, we will be discussing IR filter designed by impulse invariant method. So in case of IR filter design by impulse invariant method. So as in case of the IR filter design by backward difference of derivative or approximation of derivatives, where I use this mapping function s is equals to 1 minus z inverse upon capital T, right? So this mapping function we are used in case of approximation of derivatives method that we discussed in the previous session. So in similar manner, for IR filter designed by impulse invariant method, there are certain mapping functions that we'll be using. So first one is 1 upon s minus the pole value, that is pi. So this will be mapped to 1 upon 1 minus e to the power pi capital T z inverse. Okay. So that is the first mapping function that we can use for the conversion of given analog filter into digital form, right? So this h of s will be converted into h of z. Similarly, there is another mapping function which can be written as s plus a upon s plus a square plus b square. So here this s plus a should be same. Okay, this term should be same. Okay, so it will be mapped to 1 minus e to the power minus a capital T cos bt into z inverse. Okay, all upon 1 minus 2 e to the power minus 80 cos bt z inverse plus e to the power minus twice 80 z to the power minus 2. Okay, so this is the mapping function. Again, you are converting h of s into h of z. Okay, so for conversion purpose, you should have your h of s in this form, then you can directly convert it into h of z by replacing this like. Okay, basically this s plus a upon s plus a whole square plus b square will be replaced with this complete mapping function, that is 1 minus e to the power minus 80 cos bt z inverse whole upon 1 minus twice e to the power minus 80 cos bt z inverse plus e to the power minus twice 80 z to the power minus 2. The third mapping function, your h of s should have this form, that is b upon s plus a whole square plus b square. Here these b values are same. Okay, it should be same to apply this mapping function. So mapping function is e to the power minus 80 sine bt z inverse. It is similar to the function that we have written above. Okay, simply the numerator is different. Okay, 1 minus e to the power minus 80 cos bt z inverse. In place of that, here it is e to the power minus 80 sine bt z inverse whole upon 1 minus 2 e to the power minus 80 cos bt z inverse plus e to the power minus 280 z to the power minus 2. We will find that it is similar to the previous one, only the numerator are changing here. Okay, so it is the numerator is function of h of s. Here is simply b, that is constant. So likewise this mapping function will be utilized, okay, for obtaining digital filter by applying the impulse invariant method from the given analog filter. So let's solve some example here. So again, in this example, you have to convert the analog filter into digital filter. The system function is given here, right? So the given system function of analog filter is that h of s is equals to s plus 0.2 whole upon s plus zero point 0.2 square plus 9, as it is given in the required form already. Okay, here you can use this second mapping function. Okay, it is in that form, but if it is not in that form, so you have to bring that h of s in any one of these form. Okay, so that you can apply any one of these three mapping function to get the system function h of z, right? So here we can use by using the mapping function, which one, that second one, right? So what is the second mapping function? It is s plus a whole upon s plus a whole square plus b square tends to 1 minus e to the power minus 80 cos bt z inverse whole upon 1 minus 2 e to the power minus 80 cos bt z inverse plus e to the power minus twice 80 z to the power minus 2. Okay, so if you compare this mapping function with the given system function h of s, so in this case this small a is 0.2 and small b is 3. Okay, as it is b square here, so the value of b will be 3, so 3 square will be 9, right? So by substituting these values of a and b in this mapping form, you will get h of z. So the system function of the digital filter is, so the system function, the, you can say that required system function of the digital filter will be here h of z is equals to, here you will substitute zero point 0.2 and 3 in the equation, so 1 minus e to the power 1 minus e to the power minus zero point 0.2 t, right, cos 3t z inverse, right, cos 3t z inverse will be there, right, whole upon again 1 minus 2 e to the power again minus zero point 0.2 t, right, then cos 3t z inverse plus e to the power 2 multiplied by zero point 0.2, it will be 0.4, right, minus 0.4 t z to the power minus 2. Okay, so this is the required system function, right? And in the example we have been provided with capital T is equals to 1 second. So by taking capital T is equals to 1 second, what you will get h of z is equals to, so here I will be substituting this value, so this will be minus zero point 0.2, right, e to the power minus zero point 0.2, and if I evaluate it on calculator, so it will be 0.8187 approximately into minus 0.99, z inverse will be there, right, all upon 1 minus 2 again 0.8187 into minus 0.99 z inverse plus again 0.6703 z to the power minus 2 will be there. And if I simplify it, so after multiplying these values, so it will be 1 plus 0.8105 z inverse all upon, it will be 1 plus 1.6210 z inverse plus 0.6703 z to the power minus 2. So this is the required digital filters system function. Okay, so this is how you will be using impulse invariant method to obtain the required digital filter. Okay, let's solve another example here. So here you can see the given system function. So it is not in any one of these required form, right? So here the given system function, I'll write h of s is equals to 1 upon s square plus 3s plus 2. Okay, so I can factorize the denominator and I will get two factors as s plus 1 and s plus 2. Okay, so if you find the factors here, so is 2 ones are 2 will be there and 2 plus 1 is 3, right? So these are the two factors here. So again, to bring it in any one of these required form, you have to separate these two terms. Okay, so here you can use partial fraction expansion. So this h of s is equals to 1 upon s square plus 3s plus 2. I modified, or when I just factorize the denominator, s plus 1 plus s plus 2, and you can write it as a upon s plus 1 plus b upon s plus 2, right? So again, if you try to identify the values of a and b, so you will be using this equation: a into s plus 2 plus b into s plus 1, right? Okay, so to get the values of a and b here, so we'll put s is equals to minus 1 to get capital A, right? And s is equals to minus 2 to get capital A and capital B respectively, right? So if I am substituting s is equals to minus 1, so this will be 0, and here it will be a s minus 1 plus 2, so it will be 2 minus 1 1, so I'll get a is equals to 1, right? And similarly, if I'm substituting s is equals to minus 2, so this will be 0, so it will be minus 2 plus 1 minus 1, so I'll get b is equals to minus 1. Okay, so these two values I will get here, right? So therefore this h of s can be written as the value of a is 1 1 upon s plus 1, I can write, right? 1 upon s plus 1 will be there, plus, not plus because b is minus, so it should be minus 1 upon s plus 2 will be there, right? So if you compare this system function with the mapping formula, so it is in this first form, but simply in place of minus pi, so there are these values plus 1 plus 2, so that means pi will be minus 1 minus 2 respectively. So by using the mapping function, which one, 1 upon s minus pi tends to 1 upon 1 minus e to the power pit z inverse, right? So in this case, the values of, in for the first term, the value of pi will be minus 1, the value of pi for the second term is minus 2, right? So therefore this h of z will be, h of z is equals to, and I can write here 1 upon 1 minus e to the power, the value of pi is 1 in this case, so minus t z inverse is minus 1 upon 1 minus e to the power, value of pi is minus 2 t z inverse will be there, right? So this is nothing but the required system function, and if I am trying to simplify it, so h of z will be equals to, so it will be z inverse, in bracket I can write e to the power minus t minus 2t, right, all upon this multiplication of these denominators will be there, so 1 minus e to the power minus t plus e to the power minus 2t z inverse plus e to the power minus 3t z to the power minus 2. And since here again in example it has been specified t is equals to 1 second, if not specified again you will be taking t is equals to 1 second, right? So you will get h of z final value as, after substituting t is equals to 1 second and evaluating this equation, you will get 0.2326 z inverse full upon 1 minus 0.5032 z inverse plus 0.0498 z to the power minus 2. Okay, so this is the required system function for the digital filter. Okay, so let's try one more example here. Again, in this case, for the analog filter h of s is given, but this h of s is not in the required form. Given h of s is 1 upon s plus zero point 0.5 full upon s square plus 0.5 s plus 2 is there, right? Again you can use partial fraction expansion here to separate these two terms, so you can write a upon s plus 0.5, right, plus bs plus c upon s square plus 0.5 s plus 2, right? And again you can find it here, it can be written as 1 is equals to a s square, right, plus 0.5 s plus 2 plus bs plus c, and bracket just sending this denominator on the right hand side, right? Bs plus c in bracket s plus zero point 0.5 will be there, right? So if you compare the coefficients of s square, s and the constant term, okay, so on either side of this equation, so you can find three different equations, okay? So by comparing the coefficients of s square comma s and the constants on this either side of the above equation, we get, so see here the coefficient of s square is a here, as well as when you multiply these two terms, so it will be bs square, okay? So for s square there are two coefficients, that is capital A and capital B. So it will be capital A plus capital B is equals to, on left hand side there is a 0 coefficient for s square, okay, because there are no terms on left side for s square, so that means coefficient is 0, so that will be the first equation. Similarly for s, coefficients are 0.5 a, right, 0.5 capital A, right, plus again when you multiply this ps multiplied by 0.5 will be 0.5 b, right, and when you multiply c with s it will be c, right, so is equals to, again it will be 0, right? And similarly for constant terms, the coefficients are, so for these constant terms the coefficients are, this will be 2a, right? So it will be 2a, then here the constant is 0.5c, right? Plus 0.5c is equals to, on left hand side there is one constant, that is 1. So by solving these simultaneous equations we can identify the values of a, b and c, right? Here you can find that a can be written in terms of b as well as it can be written in terms of c, and by substituting those values here you can get the values of a, b and c. Okay, so I'll directly write down the values of a, b and c here by solving above simultaneous equations. We get the values. Capital A will be 0.5, capital B will be minus 0.5, and capital C will be 0. Okay, I can substitute these values in the h of s. So we have this h of s, a upon s plus 0.5, so it will be 0.5 upon s plus 0.5, right? And the value of b is minus 0.5 h, so here I can write minus 0.5 h. C is 0, right? So s square plus 0.5 s plus 2, so s square plus 0.5 s plus 2, right? So if you compare this one, this first equation, so it is in this required form, right? In this first form, but while the second term in this case is not in the required form, so we have to make certain adjustments here, right? So what I will do, I'll simply write this h of s as, again I will take this 0.5, this I can write 0.5 upon s plus 0.5 minus, I will take this 0.5, right? And here I can take it as s upon, just to write it down this equation I need, because there is s term here, right? Small s is there, correct? So as it is in the form of s, so we need equation in this form, s plus a, right? So for that purpose in denominator we need s plus a whole square plus b square. Okay, so for that purpose again I'll simply make this arrangement, that is h plus 0.25, as here you can see that this 0.5 is there, so 0.25 multiplied by 2 will be 0.5 if I'm taking whole square of it. Okay, so it will be h square, 0.5 h will be there, and 0.25 whole square will be there, right? And to eliminate that additional term I will simply write 1 plus 3919 whole square, right? So that the addition of those two terms should be 2, correct? So after making these arrangements here, we can have this equation. So again we need h plus 2.5 in numerator, right? So again we need to make that arrangement. So for that purpose what I will do, I will simply write h of s is equals to this 0.5 upon s plus 0.5 will be as it is, minus 0.5 will be as it is, but here I will write s plus 0.25, s plus 0.25 whole upon s plus 0.25 whole square plus 1.3919 whole square will be there, right? So to eliminate this 0.25, I will have minus 0.25 whole upon s plus 0.25 whole square plus 1.3919 whole square. Okay, so now all these equations are in somewhat required form. Okay, here it is 1 upon, so it is in this first equation form, while the second term in this second equation form, and third term in this third mapping function form, correct? But to get that third mapping function form, again we have to make some little bit adjustment here. So I'll write h of s is equals to 0.5 s plus 0.5, right, minus this 0.5 s plus 2.5 s plus 0.25 whole square plus 1.3919 whole square will be there, whole upon. So I'll just multiply this 0.5 inside this bracket with this 0.25 and make adjustment such that it should be 1.3919 in numerator, because b upon s plus h a whole square plus b square, that mapping function form we need to apply here. So this minus minus will be plus, right? So here I'll write 1.3919 whole upon s plus 0.25 whole square plus 1.3919 whole square, right? And to get the exact value here, so I need to multiply it with 0.0898. Okay, so to this term we'll be applying first mapping function, to this term we'll be applying second mapping function, and to this term we can apply third mapping function. So after applying this mapping function, so as per these three mapping function, in first term the value of pi is minus 0.5, right? In second term the value of a is 0.25 while b is 1.3919, right? Here also values of a and b are 0.25 and 1.3919. So I will directly write down these equations there, right? So I can have directly h of z as per those mapping function. So 0.5 is the constant and it will be 1 upon 1 minus, as per mapping function, 1 upon 1 minus e to the power minus 80 basically z inverse. Okay, actually e to the power 80 z inverse is there, right? First mapping function e to the power pit z inverse, that whole value is nothing but in this case 0.5 minus 0.5 is there, right? Here it is minus 0.5, so it should be e to the power minus 0.5 t z inverse will be there, right? Similarly the second, for the second term this 0.5 is constant, the value of a and b, a is 0.25, b is 1.3919, right? So according to that mapping function I can write directly here 1 minus e to the power minus 80, that is 2.25 t cos pt 1.3919, 0.3919 t z inverse in the numerator whole upon 1 minus 2 e to the power minus 2.5 t again cos 1.3919 t z inverse plus e to the power minus 0.5 t z to the power minus 2, right? And the third term here is 0.0898. Values of b and a are same, right? But we have to apply the third mapping function. 0.0898 is there, right? As per third mapping function, it is e to the power 80 sine bt z inverse is there. So e to the power minus 2 point minus 0.25 t sine 3919 t z inverse is there, right? All upon denominator will be same, that is 1 minus 2 e to the power 2.5 t, then cos 1.3919 t z inverse plus e to the power minus 0.5 t z to the power minus. Okay, so again in example the capital T value is given 1 second, so you can put, since capital T is equals to 1 second, and if you substitute the value and simplify this equation, so it will be h of z is equals to 0.5 will be as it is upon 1 minus e to the power minus 0.5 z inverse, so e to the power minus 0.5 is 0.6065 z inverse, right, minus 0.5 again in this equation 1 minus this e to the power minus 0.25 and cos 1.3919. If you evaluate on calculator, so it will be approximately 0.1385 z inverse, right, all upon again 1 minus this minus minus plus will be there. Okay, so this again if you evaluate this value, so you will get, I think it's minus only, not plus. Okay, this should be minus. Okay, minus 0.277 z inverse plus 0.606 z to the power minus 2. Then the remaining term plus 0.0898. Again, it will be 0.7663. The evaluation of this numerator e to the power minus 0.25 and sine 1.3919. So it comes to 0.7663 z inverse all upon 1 minus 0.277 z inverse plus 0.606 z to the power minus 2. If you want, then you can again simply add and simplify these terms, or you can keep it as it is, right? So this is the required system function for the digital filter. So we have converted h of s into h of z, right? So in today's session we have seen this method where we have converted the given analog filter to digital filter by using impulse invariant method, right? So for impulse invariant method we can use any one of these three mapping function depending on in which form the system function is given, right? So here we have seen the application of all these three forms, right, to the given system function to obtain h of z, right? So in next session we'll be looking at the IR filter design by the bilinear transformation. Thank you for joining this session.